You know, every big breakthrough in psychology, whether it's a new therapy or some deep insight into how our brains work, it doesn't start with an answer. Nope. It starts with a very special kind of question. We call it a hypothesis, and it's basically the bridge that takes you from just being curious about something to finding a real scientific conclusion.
I mean, think about a question like this. This isn't just academic, right? This has huge real-world consequences. So how would you go about proving if a new therapy actually works? You can't just guess. You need a formal, structured way to figure it out. And that, right there, is exactly what a hypothesis is for. So let's really break this down. All research starts with a big topic, which leads to a question. But here's the thing. You can't just leap from having a question straight to running an experiment. There's a crucial step in the middle. And that's our bridge, the hypothesis. It's the thing that takes your general curiosity and sharpens it into a super specific, testable statement. So here's our game plan for today. We're going to start with how we turn a question into a proper hypothesis. Then we'll get into its rival pair, the null and the alternative. After that, we'll figure out if we're looking for a difference or a correlation, and whether we should add a direction to our prediction. And finally, we'll put it all together and build our very first hypothesis from scratch.
All right, let's dive right in. First up, taking that little spark of curiosity and turning it into the actual fuel for your research. This is where we get formal and turn our ideas into a statement that we can actually put to the test. So what is a hypothesis, really? Well, at its heart, it's just a formal assumption about how different things, or variables, are related to each other. But it's way more than just a guess. It's a very specific, testable prediction. Your entire study is then built around one single goal, to collect enough data to see if you can confidently challenge that assumption you started with.
Okay, now here's where it gets really interesting. A hypothesis never stands alone. It always has an opponent, a kind of rival idea. And in science, that's how we test things. We set up a sort of statistical duel between two competing ideas.
And these are our two fighters. First, you have the null hypothesis, which we call H0. This is the default position. It's the ultimate skeptic in the room saying, nope, there's no effect here, no difference, nothing to see. Then you have the alternative hypothesis, or H1. This is your idea. It's what you, the researcher, actually think is going on, that there is a real effect or a difference.
A fantastic way to think about this is like a courtroom trial. The null hypothesis is always presumed innocent. It represents the status quo, the nothing happens scenario. All your data, your experiments, that's the evidence you're gathering. Your entire job is to collect enough strong evidence to prove the null hypothesis guilty, or, in our world, to reject it.
And here is a fundamental rule of the whole game, and it's a big one. You never actually prove your own hypothesis is true. I know, it sounds weird. Instead, what you do is show that the null hypothesis, that no-effect scenario, is just really, really unlikely to be true. So by knocking down the null, you're lending support to your alternative idea. It's a subtle but absolutely critical part of how science works.
Okay, so you've got your null and your alternative all lined up. Now you come to your first big fork in the road. You have to decide what kind of relationship you're actually looking for. Are you trying to find a difference between two groups, or are you looking for a connection between two variables?
And this really boils down to two main types. First, are you comparing separate, distinct groups of people or things? If so, that's a difference hypothesis. Or are you looking for a pattern between two things that can be measured to see if they kind of move together? If that's the case, you're working with a correlation hypothesis.
Let's look at some classic examples of difference hypotheses. Notice the pattern here. In every single one, we're comparing distinct groups. Extroverts versus introverts, a group that got a drug versus a control group, smokers versus non-smokers. We're always comparing the average outcome between these separate categories. Now contrast that with these. Here, we're not comparing fixed groups at all. Instead, we're seeing if two things move in tandem. Like, as the hours you study go up, do your exam scores also tend to go up? As height increases, does weight also tend to increase? We're on the hunt for a pattern, an association.
Okay, great. So we've picked our path, difference or correlation. Now we can add another layer of detail, which I like to think of as setting our research compass. Are we just going to say, hey, there's a connection here, or are we going to be bold and point in the exact direction that connection goes?
And the difference is all in the words you use. A non-directional, or what we call a two-sided hypothesis, just says a difference exists. So, the salaries of men and women differ. It could be more, it could be less. We're not picking a side. But a directional or one-sided hypothesis makes a very specific prediction. Men earn more than women. See, it's a much bolder claim.
So when should you make that bolder claim? Well, the rule of thumb is actually pretty simple. You should only use a directional hypothesis if you have a really strong reason to, based on solid theory or previous research. If all the evidence already points one way, then sure, make that specific prediction. But if not, it's safer and, frankly, more scientific to stick with a non-directional hypothesis.
All right, it is time. Let's put all of these pieces together. We have all the building blocks we need. So now let's just follow the blueprint and construct a complete, really well-formed hypothesis right from the ground up.
Let's just walk through it with an example. Step 1, we start with our question. Does a new drug improve memory? Okay. Step 2, we form our core pair. The alternative, H1, is that the drug does improve memory. The null, H0, is that it has no effect. Step 3, what's the type? Well, we're comparing a drug group to a control group, so that's a difference hypothesis. And finally, step 4, the direction. We're predicting an improvement, which is a specific direction. So it's directional. And bam, just like that, we have a complete, totally testable hypothesis.
And that, right there, is why this whole process matters so much. A well-formed hypothesis isn't just some sentence you have to write for a paper. It is the solid foundation for your entire research project. It's the tool that turns a vague curiosity into something that is focused, something that is testable, and something that is scientifically clear and powerful. So there you have it. You now have the complete toolkit to go out and build a really powerful scientific hypothesis. So what fascinating question about the human mind are you ready to test? Thanks for joining me.